A rational function is a function that can be expressed as a rational, right? A function over a function. It's the ones where you have a numerator and a denominator, pretty much. Think about rational numbers can be written as a fraction, right? Where ax and bx are polynomials, and specifically you see this little guy, bx cannot equal 0 because he's the guy in the denominator position. They look like this. These are your two basic things that will happen with a rational function. They will go like this, where they're split here, or they will do like this, where they're going the same direction. Now, it doesn't necessarily mean that they'll always be doing this. They could flip, they could be doing here, or they could both be going down, but they will either be going these directions or these directions, and you can actually slant them, so you can actually shift the whole thing and have them going kind of catty corner there. But those are your basic rational functions, and that's what they look like. And so if you have your little parent function sheet, right, from last chapter probably, if you keep moving down, rational functions was on there, right? And so this is one of your parent functions, are these rational functions, all right? Let's talk about what an asymptote is. We have talked about these before. This is a line that your graph gets infinitely close to and never touches, all right? So it is not part of your graph. It is a guideline for your graph. Think of it as your axis on your parabola. The axis on the parabola was not actually part of the graph. It just told you what you were symmetric to help you graph it, okay? These asymptotes are sometimes discontinuities in the graph if they're vertical, or they're just guidelines for eventually when you go towards infinity, you're going to be moving closer to this line. A couple things I want to point out. Vertical and horizontal, obviously what those words mean are exactly what these mean. A vertical asymptote, that's going to go this direction, right? That is actually going to be a discontinuity. You will never touch him, ever. You will not cross over him. You won't touch him. You may jump over him, but you will not touch him. All right? The horizontal are what happens at the end of the graph. I say that because there are cases where you can actually cross that horizontal asymptote and come back towards it, towards infinity, okay? So it is not a line in the sand, you'll never touch it. It is a guideline for the end of your graph, okay? But vertical, you will never touch. That is when x is undefined. You do not have a definition for x there on your real coordinate plane, okay? So let's just look at translating these guys. So taking these pictures and just moving them around based on the adding or subtracting on the inside or on the outside, just like we did with parent functions for like a parabola or absolute value, okay? So look at the first one. So this obviously is going to look like which of these? Well, if you look at the grouping here, the grouping is squared. So he should look like the one that is squared, this guy, okay? Now, like anything else, inside the parentheses is going to move it left and right. Outside of the parentheses is going to move it up and down. A negative would flip it, just like a negative flipped my absolute value v, okay? So if I were to just say, identify where these are and then graph it, since we haven't talked about the shortcuts for the asymptotes, it's often easier to figure out where that vertex type thing is going to be and then say, well, what's going to create those lines? So my vertex here is 0, 0, or the thing that I'm moving, right? You can see that the graph is not touching the x-axis and the graph is not touching the y-axis because my 0, 0 is that point of crossing, all right? So if I were to then graph this one that has now been translated, all right, then I am going to shift him around the graph. So I am going to take it, and what do you think this -1 is going to do on the inside? It's going to shift it left and right. Specifically, remember on the inside, it does opposite of what you would think. So it's going to shift it right, okay? So instead of being at 0, 0, I'm going to move over 1. All right, this 3 on the outside, well, what is he going to do to it? He's going to shift it up 3. So my new point that is going to create a crosshairs, so to speak, is going to be right here at 1, 3. And so if I were to draw a dashed line, I would draw it as though I shifted my axis up from my x side, that axis, if I shifted it up 3 and shifted it over 1. If it'll let me grab this guy here and just straighten him some, that would be great. Okay, there we go. So I am going to just do this little dashed line that represents the x-axis that I shifted up, right? And I am going to do a dashed line here because I shifted the y over. Now, other than that, I mean, it is multiplied by 2, but when you're sketching, you don't have to even worry about that for him. He would have moved from doing this little crazy thing that it does right here, this little guy and this little guy, and they're going to just do it here. They're going to do it at that cross, all right? And so it's going to look like this. It's going to be some little swooping thing. I didn't do it close enough to that. And he's going to go infinitely close to that line, infinitely close to that line. And on this side, he's going to do the same thing. Infinitely close over here, infinitely close over here. All right. So all we did is we took our shifting or transformation rules and we just moved that picture around the graph. All right. And so if I were to say, well, what are your asymptotes? Well, obviously, I have a vertical one at 1 and a horizontal one at 3. Those were created by what happened within the graph, okay? Now, vertical, you know how to solve for. If I looked at this and said, where is a vertical asymptote? Well, it's what makes my denominator 0. And you would say, well, x equals 1 is going to be a vertical asymptote because that's what makes my denominator 0, right? And so that is another way to say, where's my vertical asymptote? This is really what is affecting my horizontal, but there are other things that affect the horizontal, so we're going to talk about quick ways to solve for those as well. So for this first one that they've given us here, we have x minus 1 over x plus 2. If I were to look at this, I would say, well, this one's not squared per se, but it does look similar to what's going on in the 1 over x problem, right? He's like switched around a little bit. I want you to pay attention to the asymptotes that you can see though. Here, you can visually see that you're going to have one at -2, and you can tell that from this graph, right? But this is not really a translation of the two that we've been talking about. This guy here, well, I can see if I were to look up here that there's obviously a horizontal one going on up here, right? But again, this does not look like a translation of any of them. It looks like it's actually continuous, right? This one right here, again, it kind of looks like one of my graphs that has been moved. It looks like the 1 over x, right? But again, I still have this guy going on and I have a hole that is in here. And so you start to have functions that aren't exact translations is what happens here. So vertical asymptotes we've already talked about many times over. It's any 0 that does not have a matching 0, right? Point discontinuity. We've also talked about this. It's also called where a hole is, right? Where zeros have matching zeros in the top and the bottom. So if you can cancel it out, you're going to get this hole. If you can't, you're going to get a vertical, right? Well, how does that help us? Because we can then look at problems and say, all right, so if I cancel it out, then do I have a 1 over x or a 1 over x squared? And then it's going to look just like that thing shifted, except somewhere I'm going to have a hole as well. So let's look at this next example. Page 106, example 2. Identify the discontinuities in the graph, all right? So obviously I'm going to have 3 discontinuities here, right? I'm going to have a discontinuity at x equals -3. I'm going to have one at 2. And it looks like I would have another one at 2, but that's not how that works, right? So I'm going to have at -3 and at 2. Now, if I were to say, well, where do I have ones that cancel? Well, it looks like I have 2 that cancel, right? I can cancel out this guy here, so we know that that guy is a point. I can cancel this, but I have an issue. I still have a discontinuity at 2. And since it cannot cancel, that is going to be a vertical asymptote. Now, if you cancel everything on the top, I need to leave it as a 1. So I have reduced this, and we're going to write it as a new function. This is technically not my f function, so we're going to write it as a new function. It's going to be 1 over x minus 2. Now, this looks like a translation of one of my graphs, doesn't it? This looks like 1 over x that's been moved right 2 places, right? And that's exactly what happens to this graph. If you were to graph this one, it's going to be your 1 over x, and it's going to shift to the right. And so you are going to have that vertical right here, okay? So vertical line, that's your vertical asymptote. It is going to do exactly what you think it would do to just shift it. But there's going to be one difference in this graph. I also have a discontinuity at -3, all right? So over here at -3, right here, instead of a continuous graph, I'm going to have a hole there, okay? So instead of a continuous graph, I'm going to have a hole. And you can actually figure out exactly where that hole is by plugging in the -3. So I could plug in my -3, 1 over -3 minus 2, 1 over -5. So somewhere around -1/5 would be my y value of my hole, right? If I were to graph that perfectly, it would be at -3, -1/5. That's where my hole would appear, okay? So when you can cancel something out, it will look just like the new function, except whatever you canceled out will be a hole, all right? So I can take my translation and put it where I want and then go to where I crossed it out, and that's going to be a hole. Make sense? So all I did was translate my 1 over x function. I took it right 2 units, right? And then I put a hole in at my -3. And that's how I graphed this function. So we've already talked about finding vertical. Those are the ones that don't cancel. Finding your holes, those are the guys that do cancel. So those are all talking about when my denominator is 0. Vertical asymptote, it's a 0 in the denominator, but it does not cancel. Horizontal point, it is a hole in the denominator that does cancel. All right. So what's the pattern for horizontal? This has to do with your degrees. All right. So the first one, you'll notice that the degree on the bottom is a 2 and the degree on the top is a 1. When the degree on the bottom is larger than the degree on the top, you will always have a horizontal asymptote at your x-axis, y equals 0. So y equals 0 will be your asymptote if your degree on the denominator is larger. All right? For this one, you'll notice they are the same. Squared on top, squared on bottom. When this happens, you just take those coefficients, the leading coefficient, and those become your asymptotes. It's actually a fraction. So in this case, I had 8 in front of the x squared on top, 4 in front of the x squared on bottom. You'll see where my horizontal asymptote was at y equals 2. Okay? So it shifted it up 2 when I did that. All right? And vertical, you would find the same. The vertical are what makes the denominator 0 that does not cancel. All right? In this case, both of those actually. When you have something like this, you're going to draw your verticals from how you found those, and then you're going to find your horizontal saying, hey, do I have a shortcut? Is it bigger on the bottom? It's going to stay at the x-axis. Are they the same? I'm going to create a ratio between those numbers in front of my leading axes, my leading coefficients, right? Then we have some special cases at the end here. When the degree on top is larger, then you start to create different types of possibilities. And it's based on what happens when you divide. So if I were to divide this out, I would be left with x to the first power on top. All right? Well, what type of equation do I have when I have x to the first power? A linear. Y equals mx plus b. So it has created this linear asymptote. It's called a slant, all right? And it is based off the line that is created when you divide these out. This one is 2 degrees larger on top. What happens if I divide x cubed by x? Well, I would get an x squared. What type of graph do I get with an x squared? I get a parabola. And so I have created an asymptote parabola here, right? It's actually a function, a non-linear asymptote, right? Because when I divide it out, what's left over is a parabola. And that whole parabola is untouchable, pretty much. It's directing my lines. It's like an invisible force field, for those of you that like, Star Wars and stuff, that is just directing where that graph is going to go, all right? So let's look at this example here. It says, first we're going to graph a proper one. Proper is, think of it as a proper fraction versus an improper fraction, right? Proper fraction is where it's larger on the bottom than the top, all right? So for this, I want to find vertical asymptotes, holes, and then I want to decide what's happening with my horizontal based on those shortcuts, all right? So for my vertical and my holes, I am going to use my factoring method. I have x minus 2 on top. On the bottom, I have x minus 2, x minus 3. So my 2 here is going to cancel. So that is a point discontinuity, right? That is a hole. So I have a point discontinuity at x equals 2. All right, my 3 does not cancel. So I am going to have a vertical at x equals 3, right? And then my degree on bottom was larger. So I am going to have a horizontal. And these are always y, because if it is horizontal, it is a y line. Y equals a number. Y equals 0. Now you can see if I were to cancel that out, it's going to shift my 1 over x minus 3, right? If I canceled those, I can just take it if I want to graph it now and just shift it. It's going to shift right 3, right? It's not going to shift up or down. So my vertical is going to appear right here at x equals 3. It did not shift up or down. So when I graph this one, I'm just going to use my 1 over x graph. So it's going to look something like this, right? We're just sketching. But I have a point at 2. So wherever the 2 falls, I am going to have a hole, right? I'm going to have a hole there. So hopefully you were able to find that you did not have any point, nothing canceled. You had 2 verticals at 0 and 4, and your horizontal was still 0. Now, this is going to follow the same method on the ends. So the ends are either going to look like an x squared or they're going to look like an x, all right? In this case, they're going to look like an x squared, right? But you can test it. Let's say you don't know. You can say, well, what happens if I put the point -1, 1 in here? This will be positive, right? If I plug in negative, well, it's not going to be -1. -1, this is going to be -1 squared is 1 minus -4 times rather -1. So this is going to be positive over positive. So if I were to do this up here, he's going to be there, right? If I were to test a point in here, which side of the graph? In the middle, it's going to look like a parabola because you've got vertical on either side of it, right? Vertical on either side of it. So I can just pick a point and I can say like 2. What happens when I plug in a 2? Well, the top's just going to be 1. The bottom's going to be 4 minus 8. That's going to be a negative answer. So it's going to be down here somewhere. I'm just seeing my y value as a positive or negative, above the x-axis, below. That's all I'm doing. If you were to pick a point over here, 5, 1 over 5 squared, that's 25 minus 20. Positive, it's going to be up here somewhere. And so you can test a point to see where it's going to be if it doesn't fit the mold of one you can just translate. All right? All right, this is considered an improper. All right, it's a little bit nice because it is one that has a shortcut. All right, but it is not, the denominator is not smaller, so it's not just automatically y equals 0. Okay, since they're the same, I can go ahead and figure out what my horizontal one will be using my shortcut. And I can say when they're the same, I'm just going to use the coefficients. My coefficient up here is -4. It's always in front of my highest x value, right? My coefficient on the bottom is +1. So I'm going to have a horizontal at -4. I'm going to have this horizontal asymptote right here at -4. For my vertical, all right, I have a denominator, x squared. Can that cancel? What makes my denominator 0? Well, x equals 0 does. It cannot cancel. Why can't it cancel? This is like the most common mistake over and over and over. Yeah, because in order to cancel, it would have to cancel with this guy, and he cannot. You cannot cancel part of a binomial or part of a polynomial. These do not cancel. Do not cancel, all right? So that means he is a horizontal asymptote, right? And so I am going to have a horizontal right here. Now this is actually going to follow my shifting like an x squared would, okay? But you can still test it. Let's say you don't know. You can test something like -1 and see where it's going to put you. Is it going to put you up here somewhere, or is it going to put you down here somewhere? So you can still test points. This guy's actually going to follow your little x squared guy, and he's going to look like that. All right, he's going to follow the x squared. He just didn't shift left or right. I can actually go ahead and look at this and decide where my vertical are going to be based on the fact that I have a 0 in the denominator at x equals positive and -1. That is not, can't cancel that out, so those are going to be vertical. But then I have this situation where my degree is larger on top. So when you have something like that, you actually want to go and do long division. Now, this is not a pretty way to do long division, all right? So you want it in standard form, and just like anytime you have division, if you start at 1 degree, you need a placeholder for all of those. So instead of writing it like this, I'm actually going to have the outside in standard form. That means that -x squared goes first. I need a placeholder for my x, and I have a 1. On the inside, I have x cubed. I need a placeholder for my x squared and for my x and for my constant, okay? So when you're doing this long division, you have to account for those placeholders on the outside and on the inside. And it's actually going to be a rather quick and easy long division. So I'm going to look at this -x squared and say what do I have to multiply it by to get positive x cubed? Well, I have to multiply by -x, and so that's what I'm going to do. -x times -x squared is going to give me that x cubed. -x times 0 is just going to give me my 0. And then -x times 1 is going to give me -x. Don't forget you are subtracting, so you are adding the opposite. It doesn't matter, obviously, for the 0, but it does matter here. All right? X cubed, -x cubed will cancel. 0 and 0, obviously nothing happens there. 0x and 1x give you 1x plus 0. At this point, when your degree is smaller here than what you have here, that is your remainder. So your remainder here is actually an x. So this looks like, well, if I divided it out, I get -x plus x over what I was dividing by. Okay? This first part tells me where my oblique asymptote will be. It will be at the line y equals -x. All right? And then this kind of also reinforces what I've already figured out up here, that I have vertical ones there. Now, I also have to look at, so I decided my vertical asymptotes here, right? Here's my vertical. So I have an oblique here. It's going to go slanted. That's what oblique means. I have vertical ones at x equals positive and -1. I now need to think about my zeros. What makes this 0? Well, just the numerator. That's all I have to worry about. If it did not cancel out as a whole, wherever the numerator is 0 is going to be where I have zeros. Well, there's one number that makes the numerator 0. So I have a 0 at x equals 0. What, however, is the multiplicity of this guy? 3. Multiplicity of 3, which means it's going to cross at 3, okay? It's going to cross at 3. So when I sketch this particular graph, I am going to sketch my verticals at positive and negative 1. That's what made my denominator 0 and did not cancel out. So I'm going to do a dashed line there, a dashed line here at positive and negative 1. But I also have an oblique one. Oblique at y equals negative x. What is y equals negative x? Well, that's my one slope going down pretty much, right? And so I have an oblique that is a y equals negative x, which hopefully we can all graph, right? We have y equals negative x here. All right. And it looks like this. Okay. So this is my y equals negative x graph. Your y-intercept is 0, negative 1 slope. Okay. Now, you'll notice that this oblique is just a directional because I am going to cross it. I've already said I'm going to cross at 0, 0. I have a 0 there. So that oblique, just like the horizontal, can be crossed. It is a directional line. It's a force field telling you where you're going to graph it. So you do need to figure out on every side of your verticals what's happening. All right. So like I would pick a point here, maybe negative 2. Where is my graph going to be? That's kind of important. So if I were to plug in a negative 2, I'm going to get rid of some of this stuff right here. Negative 2, plug it in up here. Cube it. 1 minus, he's in my way. 1 minus negative 2 squared. Negative 2 cubed is negative 8. 1 minus a negative 2 squared is 1 minus 4. So negative 8 over negative 3. That's going to give me positive 2 something, right? So positive 2 something is going to be up here. What does that look like with an oblique graph? Well, that looks like this. It actually does this crazy little, I get really close to this guy, I get really close to this guy, okay? Does that make sense? And so you also know that you have something going on here. Well, what's happening on either side of it? If you were to test these points, it's going to have to cross through. And so you're here in the middle, you're going to have to do cross through him, either from down to up or up to down. You can test it. And to figure out where you are on either side of 0. On one side, you're going to be negative. On the other side, you're going to be positive. It has to cross through. It doesn't cross through more than once. How do I know that? I don't have any other zeros, right? Same thing on this side of the graph. Test a point. If I were to test positive 2, you're going to get a negative down here. And you're going to see that oblique is just going to direct it. That's beautiful. Going to direct it like that. And so your oblique is just directing that graph. And so you just need to test where it is. Am I going to be up here with the oblique? Am I going to be down here? What happens in the middle? What happens over here? But this division tells you where they are. And typically, I will say, you will have practicing on the graphs of the obliques, but I want you to basically, the main thing I want you to know here is how to find it. How do you find the oblique asymptote? You do the division. All right.